Welcome to 4.1. What are the characteristics of a discrete real-world function? That's what we're going to look at today. So we're given a scenario, real-world scenario, where we're buying a printer for a computer. It costs $80, and then we're going to pay $15 per ink cartridge. They ask us to write a function. So the first thing we might want to go to is our verbal model. We're going to have our total cost equal to, when you go up to the cash register, you'll hand them your printer. So cost of printer. And I also want to put our units here because that should help us to distinguish that everything comes out in money, because that'll be total cost. Along with the printer, they will add what? I hope you're saying $15 for every ink cartridge that we buy. So when we have the per, we know that that's a fractional unit. So it's dollars per ink cartridge. Maybe I'll just put per one ink. And I'll go ahead and put the 15 here. And the 80 here. Okay? Now, we have to get rid of that ink down there. We can't have a unit that's being divided and try to add it to this. Order of operations would cause us to have to get the division worked out first. So unit analysis, we need to multiply this by the number of ink cartridges we buy. So if we buy 2, it would be $30 that we add to the 80. We can see here that our ink would cancel, and we're going to end up with dollars plus dollars. That's exactly what we want. Now let's go ahead and get our letters in there. Remember, this is our dependent variable, so whatever we use for our number of ink cartridges, it will be influencing this. So let's just go ahead and use N for number of ink cartridges. We'll write up here N equals number ink cartridges. Should always define your variable. Okay, so we have 15 times N. We don't put the dollars in because we're going for our algebraic equation now. We have 80. That doesn't change with our number of ink cartridges. It's only this that gets multiplied by the number of ink cartridges. So we just add the cost of the printer. And now that will equal our total cost, which is a function of the number of ink cartridges. So we can use C for cost, but we need to show that it's dependent on the number, so we write it like that. Now our dependent variable is always graphed on the y-axis, because y is dependent. X is independent. And the way we know that is that the number of ink cartridges determines the amount of price that we pay. So we went ahead and we plugged in 0 into that equation, 80 plus 15N. If we plug in 0, it would just be $80 for the cartridge. If we have one cartridge, 15 plus 80 would be 95. And from the sequences we've done in class, you're probably already saying, oh, you could just add 15 going down. That's fine too. Or you can plug in these values for the number of cartridges and get your answer and work it this way. There's patterns everywhere in math. Do it the way that your brain likes. Okay, so with 0 cartridges, it's $80. Let's just go 20, 40, 60, 80, 100, 120, 140. Okay, let's plot our points. At 0, we're at 80. At 1, we're at 95. So right about there. At 2, we're at 110. At 3, we're at 125. 4, we're at 140. a tendency in your mind to connect those. But would that really show the amount of money you're going to owe? Remember, you're showing the cost down here. Oh, I'm sorry, not the cost down there. Whew. The number of cartridges down here. And your cost over here. We should always label that. Okay, so if we think about it, in between the points, can we buy a half a cartridge? I hope you're saying no. So our domain needs to be limited to distinct points. 0, 1, 2, 3, 4, and it could go on. Now, why can't it go into the negatives? Be prepared to discuss that in class. The range, we started at $80, and it's not going to fall between either, as long as there's no sales tax, and we aren't worried about that in this problem. So 80, 95, 110, 125, and 140. So there's a name for this kind of a function where it has distinct points. You can see it on the graph. You can also see it in the domain when it's listed as distinct points. And the name for that, oh my goodness, earthquake. Shoot! The name for that is discrete. If they're disconnected points, they're discrete. This is real world because we're talking about something that could actually happen out here, and you'd have to predict your cost. Distinct points, discrete graph. Distinct points in your domain and range, discrete graph. Now we might look at what would happen if we went to the store and the price went up to 90. On the graph, it would be very easy to just increase each of those by $10. Okay, that's in case the sale ended. Now, it's also called a discrete linear function. Hopefully you remember from some of the sequences we've been doing that linear occurs when we're adding or subtracting the same amount between our points. In that problem, we were adding 15 between each one. We've done a few sequences like this. Plus 3, plus 3, plus 3. You found your difference, common difference. That's what makes it linear or arithmetic sequence. Now we can predict our next two terms by continuing the pattern. And now it says find the 100th term. Well, we know if we have the 99th term, we can just add 3. So we could put A100 equals A99 plus 3. Problem is, I might not give you that 100th term. So you might have to find it like with the first term. In class, we talked about this. Remember, the first term can be used to find any term. You guys even found it with other terms. We're just looking at the first term. So we can take that first term. How many of these does it take to get down here to the 6th? This is your 6th term. How many of these are there? If you said 5, you're right, because we're going from the first term, not from the beginning. So it would be A1 plus 3 times, to get to the 6th term it was 5, to get to the 100th term it would be 99. Now there's one more direction we went with it. We said, well, let's turn this into a complete function. And we went back this direction to the 0th term, because functions go to the 0th term so that you can locate your y-axis. That would be your 0th term. Here's your first term. So we'd like to go back to the 0th term. That means we need to figure out what plus 3 is -5. Would be -8. And then if we go to the 0th term, we don't have to put it in here because we're writing our function rule, but if it's the 0th term, then we do have the same number of this pattern as it is the term number. So it would be 3 times 100. Okay? So if we switch this over to a formula, we would say f of n, whatever we're looking for, is the 0th term plus 3 times 100. Okay, we're getting clear, or not 100, it would be 3 times n, because it's whatever number you're looking for. So that takes us to our linear formula that we've talked about in class. When we put it on the graph, our y value is f of x because it's a function of x. This would be x now. 3 is how much we're increasing from one to the next. And our 0th term is whatever we start at. For this one, it would be the -8. Okay? If we flip that around, 3x minus 8, that's a more common way that we see it on our graphing. mx plus b. Now look back at our real-world problem here. Do you see where we could have written this as c of x or f of x equals, switch these around, 15. Now since that's an x, we'll put an x here, plus 80. There's our y-intercept, and there's how much we're gaining with each x value. That's our slope. Okay? They're very closely related to these functions that we've been playing with in class. I hope you've been there. This is just that function being graphed. So if we were to graph it, remember in class we would go ahead and graph these. So it'd be at first term it's -5, second term it's -2, third term it's 1, fourth term it's 4, fifth term it's 7. So we just keep going like that. You can see it's a linear function. And again, we don't connect it because we can't have a term halfway between the terms. It's first term, second term. You wouldn't have a half a term in there because if you wrote another number, it would become a new second term. Now we do like to take it back to the 0th to show the y-intercept, and it lines right up. Okay, so sequences have a common difference, add, subtract. Hopefully you've been in class seeing that. And we also talked about how sequences are a linear function where our domain is restricted. Shh, they're discrete separate points too. Remember, discrete means separated. See you in class.